Hello and welcome to VHDL lectures. My name is Najim Lawal, and now we shall be discussing VHDL intermediates. To guide us in this discussion, we focus a little bit on counters, shift registers, memories, generics, and generics. Counters in VHDL are perhaps the most basic thing that you should be able to do and be able to do efficiently, because with counters you'll be able to go through a lot of finite state machines. You'll be able to know perhaps you'll be able to synchronize with the clock of the system. You'll be able to know in terms of human seconds and in terms of clock cycles what is going on and which stage of the implementation you are in. So for example, if you have a modulo 25 256 counter like this, and then you know from basic bits and logic level that you have 8 bits to be able to count between 0 and 255 and back to 0 again automatically. So if you are going to use this, if you have the intention of implementing this, then you might have an implementation that looks like this, in which case you have the library IEEE, and then you have the logic, standard logic 1164 package, and then also the package for numerics, arithmetic. With this, you are, after calling and making references to these packages, then you can start by declaring your own entity, implementing an architecture to do this. For this, I have a clock that comes in, and with this clock, I will be able to update on every edge, positive edge, or if I choose negative edge, rising edge of the clock. Then I would like to update my counter. I would like to increment by value of 1. So I have clock coming in, and then I have a counter value as a buffer going out. Remember, buffers are a way of being able to send out data through an output, but at the same time reserving the rights to update it. So you are able to read and update, and the consumer is only able to read. So now I have an architecture RTL attached to this modulo 256. I have a process within it after the begin instruction statement after the architecture. Then I have another begin attached to the process. So now I have my process being sensitive to the clock. Right now I have no counter enable or reset. It's just a way of simply analyzing and saying that if you want to implement a counter in VHDL, this is how I can do that. So upon the rising edge of the clock, I would like to update the counter value by 1. So moving forward from counters, perhaps we like to do something like a shift registers, in which case you have an array of data, and then you like to shift them to the right and to the left, perhaps 1 step at a time, or perhaps 2 steps at a time, or multiple number of steps at a time. To do this, perhaps is very simple, because you need to know what are the constructs that are available in VHDL that can assist you in doing this. And this can be done for a bit vector, and it can also be done for an array of integers, an array of bit vectors again. So now let us just focus on the simple case of bit vectors. As a matter of fact, let us just assume that there are only 4 bits in this bit vector. So now to do this, we say that shift register is a systematic approach to copying data, perhaps to the right or to the left, among the elements of an array. Shift registers work on array of scalars or array of vectors, and then the values can be copied to the right, to the left automatically using your own implementation, or simply calling the libraries that are available in VHDL. And of course, we use the library IEEE, and we use a package called standard logic 1164.all. Here is an example in which I would like to shift to the left, one step at a time. Hence, I would like to increase or multiply the value by 2. Okay, since this is a standard logic vector with the most significant bit on the left hand side and the least significant bit on the right hand side, so shifting to the left is another way of multiplying by 2. To implement this, I have a clock, I have a reset signal, and then I have a that is active low, and then I have a data coming in, a shift enable that tells me when to shift or not, and then all these are coming in, and what goes out is the data or the current value of the shift state of the shift register. Now I have my shift register implementation. So I have an architecture attached to the entity, and this architecture is now going to be implemented using a register, a shift register, and now which is also 4-bit, 3 down to 0, the same data type. So now I create a process within this architecture. This process is going to be sensitive to the clock, and it's also going to be sensitive to the reset. Now, like I mentioned, because I know that my reset is an active low reset, in order to remember, I put an N at the end of the reset, at the end of the name of the reset signal. So when the reset signal is low, if the reset signal is low, then I would like to nullify or set all the signal shift register shift_reg signal to 0. Now, upon subsequent events on the clock, and when the event finalizes with the clock value being 1, then I would like to shift. But this can only be possible if the shift enable signal is active, it's 1. So here I have 3 alternatives to implementing shift register, one of which is simply implemented by myself, in which case I say that shift register shift_reg, the internal signal that I've created, is 3 down to 1, and then I copy the last value, the old value on the lower bit. From 2 down to 0, I copy them to 3 down to 1. Okay, and then I need to update the least bit. So to do that, I jumped to the last statement before the if, in which case I say shift_reg logic, the least significant bit bracket 0 is updated given the input value data d_in. There are 2 other alternatives, in which case I can say that shift_reg should be assigned given a function called shl shift left logic or shift left, which is takes as an argument the data that I would like to shift, the source of the data that I would like to shift, and how many steps I would like to shift it. Also from the IEEE package standard logic 1164.all, I also have an operator that is behaving also more or less like the shift logic function. It's called SLL, and it's shift left logic, which is a way of saying that shift the operand to the left by the number of bits or number of steps defined by the operand to the right. So now I have shift_reg SLL 1. So with all this, I can close my if statement as a function of which is activated based on the shift enable, and then I can close my clock statement, and I can also close my process. When within the architecture, now I can update the output data shift_out, giving the current data of shift_reg. So this is a very simple way of implementing shift register, and this example can be extended to shifting an array of 100 bits or in which case, or another array of vectors in which each element of this array is a vector, for example, of 8 bits. Of course, the implementation given your synthesis tool can be very, very large and consuming a lot of logic elements. So perhaps you don't want to do that. Be shifting 256 logic level and 256 addresses, and at each address is about 8 bits. Perhaps you don't want to do that. To be able to do this kind of stuff efficiently, it's advisable to use memories. And memories in VHDL can occur as registers. So every time you declare a signal, you have a constant, you have a variable, or even your port, for example, the buffer that we used in a few minutes ago. Even your port in itself, they are registers because they hold values. You also have random access memories, which are part of resources in current state of the art, even the normal FPGA that you can buy today. You can also implement RAMs as a form of ROM. The difference between the RAM and the ROM is that there is no data coming in and there is no data enable or write enable. So when you create the RAMs, or when you create the ROM, the same way you create the RAM, you define them as constants, and then you also assign the value to them. So they get their value at the beginning, and then you can only read them forever. You cannot update them. So that is the basic difference between RAM and ROM. And RAMs and ROMs are can be implemented using data arrays that you can define by yourself, or you can use predefined macros that are available from the FPGA vendor system synthesis tool. So there are many ways to implement memories in VHDL. One approach is to implement single port. Another approach is to implement them as dual port, or you can even have dual port as true dual port, in which case you have independent read and write at different ports. So here is an example from Xilinx of how you can implement true dual port, in which case you have independent accesses to port A and port B. And here is another example of a single port. When we talk about true dual port, you need to be able to know that you should have a way to make sure that the data is valid. There is no problems with the addresses. You are not reading at the same time you are writing, and then there is indeterminacy in the value of the data that is being written or being read. To do this, we have an address contention, which is a way of defining who goes first. Should we read first or should we write first? One way to do that is to say that each port have non-overlapping address and data paths. So what we mean by that is that if you have a memory block with 100, for example, 100 address locations, then it means that port A can be restricted from 0 to 50 to 49, and then port B can be limited to write and reading from 50 to 99. So we will make sure that the address counter on port A can only count between 0 and 49, only the upper 50 addresses, and that the address counter on port B can only begin to count for reading and for writing from address location 50 all the way to address location 49. So we have non-overlapping data paths. We have also commands that says that what to write first. So when you create a memory, you like to define that this should be a write first memory, or this should be a read first memory. We can also write to a particular port and read on the other port, or you can read or vice versa. So here are some resolutions for address contention. So data path 1 only reads and writes to port A, and perhaps it has no memory or address overlap with data path 2, which only reads and writes to port B. Data path 3 reads and writes to port A and read from port B, and data path 4 writes to port B and reads from port A. So here is an example in hardware VHDL about how to implement a memory. Here is an example in VHDL about how to implement memory that has 8 bits at each location, and at each bit we only have four logic levels, 4 addresses. So we have address location 0, address location 1, address location 2, and address location 3, and at each address we have 8 bits. So to implement this, we only need 2 address bits, address 0 and address 1, and then we have data in that is 8 bit and data out that is 8 bit. We have a write enable signal to know when to write or not. Here is an implementation, or here is a schematic about how it looks. So we have clock coming in, and then we have all the addresses and signals and the enable control signal and the output port. Here is another example in VHDL that says that we would like to implement a memory block that has 32 addresses, and at each address we have 16 bits data. So on the input and on the output we have standard logic vector 15 down to 0. Because we are going to have 32 address locations, then we probably need 5 down to 0 address counter or address bus. Then we need a clock, and now we have a write enable on the active low. Okay, that is active low. So that's why we put _n as a convention to remind us in the future that this is an active low signal. So to implement this, we can do something like this, that we define a new memory type, and this new memory type is of type. It has 32 addresses. So now we have 31 down to 0, so that's the address location, and at each address location we have standard logic vector 15 down to 0. And now we declare a signal of that data type, the new data type that we have just created. Now we implement the architecture by writing begin, and inside this architecture we have a process that is sensitive to the clock. So whenever there is an event and the event ends up with the value of the clock being 1, and if the write enables signal is low, because we have an _n at the end of it, then we like to write the input data to the given address. And now to be able to write to the address, we need to convert the address, because the address is given as a logic vector. And now our data type, the RAM type, is given as a function of integers. So now we have 31 down to 0. These are integers, whereas our address bus is standard logic 4 down to 0. So we need to convert this standard logic vector 4 down to 0 into an integer. So after the conversion into an integer, then this address location, we write the input data. All the time, it is possible at all time to read the data in the memory block. And to do that, we convert the address again to an integer, and then we read the memory array location, which is our signal. So now signal is no longer just a vector. I mean, it's no longer just a single memory location, but it's actually a memory block. Here is an example of how to implement a ROM. we once again make reference to the library IEEE, make reference to the 1164 standard logic package and another package called standard logic unsigned. Now we define addresses and then the address bus and then the output data bus. We have an implementation here that says that we would like to define a new data type called ROM table that has addresses that goes from 0 upward direction to 3, and at this address, at each address location we have 8 bits. So now we define a new signal, but this signal is a constant. So we have a constant ROM table, ROM content of type ROM table, which we have just recently defined, and then we say that each should have this kind of data in it. Okay, so we assign data to it at the point of creation. Then we have an implementation of this architecture that says that whenever the address bus changes, we convert the address bus into an integer, and then we look up the the ROM content, whatever value that corresponds to the current address bus, we write it out to the data. So this is the way in which we can implement a ROM. And as you can see here, we don't need the input data, we don't need the write enable or not. All we need is that we need the address, and then we automatically look up the ROM content table or the ROM content ROM memory locations, and then we write out the data. In VHDL, it might be possible or it might be necessary for us to implement the same thing over and over again. And to support us in doing this, we have a support for for loop, which can be synthesized if we can statically determine how many iterations that is going to be performed. So this is not dynamically on the fly, given that you like to implement, you like to perform a for loop n times, in which n is a variable, or in which the value of n comes from an external port, okay, or it's updated or calculated on the fly within a process. No, that's not meant to be synthesizable. But if we know that we would like to implement a for loop that iterates for a specific number of time and the same number of time all the times, then we like to say that yes, it can be synthesized, and the synthesis tool will simply go ahead and blow it up and implement this. So here is a syntax for implementing for loops. We can give it an optional label. Of course, we use the keyword for, and then we have parameter in a given range, and this range needs to be static if we like to synthesize this for loop. Otherwise, we can use it in a test bench. Then we have the loop keyword. We put our statements that we like to implement. It can be one, it can be many, and it can even, then we end up by closing it by saying that end loop and then the optional label that we gave. So here is an example of how to implement a for loop. Here we have this for loop that is going to iterate 4 times between 0 up to 3. To implement this, we have a process that is sensitive to a signal A. We implement this process with the begin command, and then we would like to generate an output Z for this, and we say that at the beginning we set all the values of Z to 0, and then we implement our for loop by saying that for I in the range 0 to 3, if the value of A is the signal that this process is sensitive to. If the value of A equals to I, then Z at location I is 1. And we end the if statement, we end the for loop, and we end the process. So here is a for loop construct that can be implemented and synthesized by by the VHDL synthesis tool. The for loop command can take advantage of some basic elements in VHDL like the attributes. Remember, we have been using events on clock, which is a special signal that can be used in synchronizing the clock levels and the implementation of a particular process. But here we can also have other attributes on signals, for example, or on signal data type, for example, high, low, left, right, and range. So in this case, if you like to, we can use a range, or we can use the high and the low. So this implementation of a for loop is the same thing as the previous one, except for the fact that we are now using attributes that are attached to a particular data type or a particular signal. So now we have the essential part is for loop for I in A low to A high loop, and then we have an implementation. What this does is that we now have a for loop that we don't know the range, and this becomes difficult for the synthesis tool to implement, okay, because we don't know at any point A low can be 1 and A high can be 7, and at another point, depending on the data or the signal type, A low can be 0 and A high can be 50 or 64. So if the value of A or the data type of A is known at the beginning, then the synthesis tool can implement that. But if the value of A can change, or the data type of A can change due to some reasons, then we can have, it may lead to some problems in the synthesis tool being able to synthesize this particular for loop construct. Now we know a little bit about for loops, but for loops can be extended to be able to instantiate a lot of components, and a lot of statements can be implemented just like the normal for loop. So we can extend it into generate, and here is a simple description. If a statement is to be implemented or a component is to be instantiated many times in the same architecture, then the generate command is very, very effective. And what we can do now is that we can give the generate command a label, and each of the statements or implementation in this for generate can be given a label. So the generate command is actually a way of restricting the for loop into being synthesizable. So before, in an attempt to use the generate, it's a way of ensuring that you have a statically determined number of iterations that are going to be implemented. So you can always think that the generate command is just a subset of the for loop command that is synthesizable. So here is an example. If I would like to implement a 4-bit adder from a 1-bit adder implementation, then I can use the for loop generate, and here is my entity. I have A and B, the operands that I would like to add together, the carry in, and then the sum, the result of the addition, and then the carry out. To implement this, I have a component at a 1 bit that has a 1 bit coming in for A, for B, and then for carry in signal, and also for 1 bit going out for the sum and for the carry out signal. I instantiate this, I make a reference to this component, and then to be able to do this using the for generate command, then I would like to have I implement my architecture. To implement this, I need a signal that can add all these components together to make 5 bits. Okay, because adding 2 4 bits together has the potential of flowing into 5 bits. So now I would like to create signal C chain that has a standard logic vector 5 down to 0. Then I assign the carry in, the input carry in to C chain logic level 0, and the carry out to C chain logic level memory location 4, or bit vector location 4. Now I have a label for my for generate, which iterates from 0 to 3, and then I have a label for each other 1-bit component. Now I have a relational mapping, port mapping, that says that I would like to map for each location of the input data, input bit operands A and B and carry chain. I would like to map them directly to the other 1-bit. So for this will be implemented and rolled up in a manner that says that when I equals to 0, A subscript 0 will be assigned to other 1-bit component 0, and this will be rolled out as many times as 4, because I like to have other 4-bit. This can be implemented in a clear manner, but they actually do the same thing. But essentially, because I'm having a carry chain, the last statement here, which is shown in red, is a way of saying that my carry out is actually to the next level. So by combining the generate, for generate, we can have a statically implemented, or we can have a very compact VHDL implementation. Now, there's another construct that can be useful in VHDL. It's actually very, very useful, and we refer to it as generics. Generics are a way of having perhaps a dynamic implementation or multiple implementation of a particular construct. For example, if we have at the 4-bit right now, that means at the beginning we specify that we like to have 4 bits. But then what if we simply have at the n bit, in which case the same construct, the same compactness in the implementation that we have just seen can be used as many times as we like. Okay, so generics are defined at the entity level, and generics can also be updated. Generics can be updated also at the entity level, but they are constants within the body of the entity, within the implementation of the entity. They can be updated at the higher level where this entity is being implemented or is being instantiated as a component. And if the values of this generic are not set at the higher level, then the default value, if one is provided during the current one, during the entity that defines them, will be taken. If not, 0 will be taken. Generics declaration are optional, and their port mappings are also optional. So generics are used mainly for delays, bus width, counter range, frequencies, and other things that you might want to change on the fly, or you might want to change between different implementations. So you might have an implementation for 8-bit, you might have another implementation for 16-bit or 32-bit or 128-bit. So here is the syntax for generate. You give it a name, you give it a data type, and you give it a default value. So here are some examples. Bus width is an integer of value 8. My Boolean level, my level is a Boolean data type that has a default value false. My delay is a time that has value 5 nanoseconds. So now we can combine generics and generics together, okay, And what this means is that if we go from counters, combining generics and generate together means that we can have a counter of any value. So we can have an implementation with the same implementation, simply changing the generic. We can have a 8-bit counter, we can have 32-bit counter, we can have any number of bits level counter. And then, so here is an example or a question. How can we create 64-bit adder? And perhaps how can we create, without doing too much work or changing of the module, how can we create one 28-bit adder? Or in simply put, how can we create an n-bit adder? Okay, where n, of course, is greater than 0. So maybe 1-bit adder or 1000-bit adder or 200-bit adder or 256-bit adder. So here is the hint that says that we should use or take advantage of the VHDL constructs, generics, and generate. And here is an example of how we can do this simple question. So we have entity at the n bit, okay, and we have in this construct a generic that says n is the integer and the default value is 100. So when we instantiate this component, this entity in a higher level, if we do not give n any value, then this n bit adder will automatically become a 100-bit adder. Okay, so now we have input data A and B that are of data size n number of bits. So they have standard logic vector n-1 down to 0. So we have n number of bits in each of them. We have the carry in, we have the sum, and we have the carry out. The sum also is of n number of bits or number of logic levels. So now we have n-1 down to 0. So we can implement this architecture in an RTL that we attach to this. We can implement an architecture attached to this entity simply by instantiating adder 1 bit, which we have seen before, and then also we implement a signal C chain of standard logic vector n down to 0, because our carry chain needs to be at least 1 bit higher than the number of additions that we like to do. So here is the continuation that says that we have a carry chain 0 attached to the input, carry in, carry chain out attached to the highest bit or highest position of our carry chain signal. Then we have this for generate construct. We give it a label called gen, and in this for generate construct we now have a component called adder 1 bit. We give it a label called u. So for each adder 1 bit, here is our port mapping that says that for every bit of A, we attach it to the input bit A, to a particular bit location A, which is given by the I in the for generate construct. And so here is our implementation. It looks very, very identical to the 4-bit adder that we did a few minutes ago. And in this implementation, when somebody instantiates adder n bit in another hierarchy, at a higher hierarchy, then we have a possibility to simply change n to whatever value we like. So if we change n to 100, then we have a 100-bit adder. If we change n to 64, then we have a 64-bit adder. Change n to 32 or to 256, then we have such number of adders. So now we have seen the relationship between counters, shift registers, memories, and how to implement using generics and generates. So these are the intermediate things that we like to use on daily basis as much as possible in order to make your work and the future use of your project very useful and efficient, it might be good to start incorporating generics and the generic constructs in order to minimize the number of logic blocks and resources that your design will be using. It might be very good to start using memories and to start using ROMs so that you don't need too many flip-flops. And of course, everything boils down to registers, and registers that are updated as a function of time or reference of clock. We call that counters. So this brings us to the end of intermediates. Thank you for joining us.